Okay, thank you. So I'm going to talk about radio wave detection of neutrinos. This has been very nicely introduced by Dimitri in the previous talk. Uh, I'll mention that what we're specifically targeting. So Dimitri mentioned that they target the interval of maybe TeV to going up to PeV neutrinos. What we're interested in is, in particular, cosmogenic neutrinos. So these are neutrinos that are produced via the so-called GZK effect, where an ultra-high energy proton interacts with a cosmic microwave background photon. And ultimately, what that leads to are muon neutrinos and electron neutrinos that have a typical energy of around 10 to the 17th electron volts. So we're probably about a factor of 3 or 4 orders of magnitude higher than what Baikal, for instance, is targeting. What's shown in this plot is basically the horizon for various cosmic ray tracers. So, for instance, a proton has an observable distance at an energy of about 10 to the 20th electron volts and higher, of about 10 megaparsecs, which places it at the limit of the local galactic group. And again, this is precisely that GZK effect, which ultimately leads to the neutrinos that we're most particularly interested in. So, what are the strategies for actually detecting these very ultra high energy neutrinos? What we're going to do is we're going to use the same Cherenkov technique that Dmitry just very nicely outlined, but we're actually going to use, instead of detecting Cherenkov photons with Hamamatsu photomultiplier tubes, we're actually detecting Cherenkov photons in the radio regime. So the various schemes that I'm going to focus on here are schemes where there's a neutrino, for instance, that interacts in an ice target, not a water target. Remember that since we're going to use radio waves, we need a very radio transparent medium, and that excludes, for instance, salt water, and it also excludes, unfortunately, even fresh water because the high dielectric constant. So you're looking for a neutrino. It interacts in ice, and you can imagine three different strategies to detect that neutrino detecting in ice. You can either have a so-called synoptic strategy, where you place your radio payload above the surface of the ice and you scan down. That has the advantage of a large scanning volume, but you're very far away from the vertex. You can imagine putting radio receivers into the ice. You drill holes and you bury radio receivers, and that's the strategy followed by the ARA experiment. Or you can imagine a strategy where you actually put radio receivers on the surface of the ice. And in that case, for instance, if your ice is sitting over a seawater substrate, you can imagine looking for signals from a neutrino interaction which reflect off of the seawater substrate and then back up to your receiver array. And that's the strategy which has been followed by the Ariane experiment. So here, here is a summary of the various experiments which strive to detect neutrinos. The first five of these are experiments which use an ice target. I'm going to talk a little bit more in detail about the RET experiment, which uses, instead of detecting Cherenkov radiation, actually uses a radar technique to sound the shower produced by an interacting neutrino. Beacon and Tarogi M, these are experiments which actually scan down from a mountaintop, and it's looking for radio signals that are produced, for instance, from a tau neutrino, from a tau shower, or a tau meson or tau lepton decay, which is produced by a tau neutrino. These are respectively, there's a prototype in California for Beacon, and there's a prototype in Antarctica for Tarogi. I just mentioned them here for completeness, as well as the ERA and Grand 200X, 200K experiment. And these are ERA and Grand 200K are looking for radio signals produced by a neutrino which interacts in the atmosphere, but at a very glancing angle. So you can look for Earth skimming radio signals. Owing to time limitations, I'm going to focus on the in ice target experiments, namely the first three of those enumerated above. And I'll mention this is an idea that originated with Markov and Zhelyeznik at INR Moscow. Okay, so the Ascarian radio array is the first of the in ice experiments that I'm going to quickly mention. So the idea again is that you have a neutrino, it interacts in ice, and in principle, in fact, there are two possible ray solutions that will propagate from the source to your receiver. There's a so-called direct solution, and there's also a refracted solution. And the fact that you have two signals that arrive at your detector separated by something like 100 to 200 nanoseconds is a very powerful and sort of irrefutable signature of an in ice neutrino interaction. So most of the backgrounds are, for instance, coming from the surface. But if you see this double pulse signature, it immediately tells you that what you're seeing is an in ice neutrino interaction. On right is shown the station detail, showing the radio receivers buried at a depth of about 200 meters or so. And here are the flux limits that ARA has been able to produce from their most recent publication. What's shown in black are the flux limits. What's important, I think, is that the shadowed band shows or indicates to you what the theoretical prediction is. So you see that even with the current experimentation, we're still about a factor of an order of magnitude away from the theoretical prediction. This can be improved and will be improved by looking at more data. This uses only about 10% of the available ARA data set, and also the lifetime of ARA will be extended by about another factor of 2 over the next 3 or 4 years. Okay, the other another experiment that I mentioned was the surface strategy. So here you put antennas uh, very close to the surface, and again, you can measure, in principle, a series of different sources. You can measure neutrinos interacting in the ice. You can measure cosmic rays that are produced by sorry, you can measure air showers produced by cosmic rays interacting in the atmosphere, and you can also measure radio signals produced by decaying tau leptons that are the result of tau neutrinos interacting in rock from a nearby mountain. And to date, the Ariane experiment has actually measured cosmic rays, although it has not measured any neutrinos. As a proof or a demonstration of performance, what they've done is they have measured their polarization sensitivity. So you need polarization information to reconstruct the Cherenkov cone. You need if you like, the theta and phi components of the Cherenkov cone to measure the actual neutrino geometry and trace that to a point in the sky. Um, the angular resolution on a neutrino interaction. So if you're trying to measure, for instance, the angular resolution relative to a source, that angular resolution is measured at about a degree in both the elevation as azimuthal planes. The polarization measurement relative to measurements made in the lab is good to about a few degrees, which is quite good if you're trying to actually reconstruct the incident neutrino direction. Okay, the final strategy that I'll mention again is the so-called synoptic strategy, which to some extent has generated the most interest of late for reasons which I'll detail in a second. Here you take a radio receiver array, you put it up on a balloon, and again, you're sensitive in principle to air showers that are produced by ultra high energy cosmic rays. There you get radio signals, so-called geomagnetic signals that will propagate down to the surface, and then they will reflect back up to the gondola. When they reflect on the Earth's surface, on the ice surface, that signal should undergo an inversion of its polarity, which turns out to be very important. Signals coming up from the ice, for instance, from a tau neutrino, those will suffer no such inversion, and there you get a direct signal from an in-ice interaction of a neutrino. And in addition, there's a third class of event where there are so-called direct ultra-high energy cosmic rays, uh, which will interact at glancing angles, and those produce direct radio signals. Notice that the radio signals produced by direct UHECR have an inverted polarity, opposite polarity relative to reflected UHECR. Again, in the second case, there's an inversion due to the effect of the ice having a higher index of refraction of air. Okay, so here again is a sort of a summary of the different signal types for Earth skimming neutrinos. For instance, you have an expected polarity that looks as shown in the figure on the left. And for a reflected cosmic ray signal, you have this inverted polarity, which and the difference between these two is clearly obvious. Okay, so the Anita experiment again is sensitive to these various types of signals, and a picture of the balloon itself as it's being filled for operation is shown in this slide. Here you see the Mylar balloon itself being filled with helium prior to launch, and what's shown in the lower left is the gondola. So this is actually a picture of this instrument. So the instrument consists of high resolution quad ridge horn antennas. Everything, of course, is solar powered. The total weight budget turns out to be about 600 kilograms or so. And again, this is another picture. This is the first launch of Anita, and you can see the gondola at the very bottom and the balloon bringing it aloft. By the time the balloon gets to float altitude, which is about 38 kilometers, the balloon is inflated to something like the size of the Rose Bowl or Luzhniki if you're in Moscow. Okay, there have been actually now 5 different Anita flights. There was the initial prototype, then Anita 1 in 2006, 2007. And as time goes on, you can sort of see how the payload gets increasingly complex. The most recent flight of Anita 4, happened in 2016. And the most recent physics results to emerge from Anita 4 were just released in the last couple of months, and I'll talk about those in a second. So perhaps the most interesting thing that has been generated by the Anita flights is illustrated here. So what's shown here are a series of waveform captures. And what you see here are, for instance, in the upper left, this is a standard ultra high energy cosmic ray signal. It shows the polarity expected for a reflected signal. These are so-called direct ultra high energy cosmic rays. It also shows the same polarity, predominantly negative, expected for a signal which is Earth skimming but does not reflect off the Earth's surface. So this is a standard reflection. This is Earth skimming. They all have the same polarity. In the lower right is a signal which has about the same upcoming elevation angle as the standard ultra high energy cosmic ray at this sort of elevation angle. However, it has clearly inverted polarity. And there are a couple of events that have been observed of this type in the Anita dataset, and these are the so-called anomalous or mystery events. So the question is, why is it that this signal, which should have been reflected and inverted, has a polarity opposite to what most of the events, to what the pattern which is indicated by most of the events that Anita observes. Now, a couple of caveats about this. The fact that the event is mysterious. In fact, there were 2 of these, one observed in the Anita 1 flight and one observed in the Anita 3 flight. The fact that they are mysterious is based on only one observable, namely polarity. It's just the fact that this signal is predominantly up and these signals are predominantly down in their polarity. So the first caveat is that, again, the mysteriousness is based on only one observable. Then the question is, well, maybe what you're seeing is really a neutrino, because then it would not have this inverted characteristic. But that possibility is ruled out by Earth absorption. At these sort of incident angles of 30 degrees, 35 degrees, the chord of Earth that the neutrino will go through is too large, so that, well, it's so large that the neutrino will have to have interacted before it can possibly produce a signal. The second caveat is that the waveforms that are shown are only shown after unfolding the Anita detector response. That is to say, they are so-called deconvolved. Um, and To that extent, all band-limited signals will look in principle identical. And the mystery events are otherwise indistinguishable from ultra-high energy cosmic rays and their FFT, etc. So what you don't see are the original waveforms before deconvolution. This, of course, is the right thing to do, but you rely on that mathematical procedure to be correct. Um, then the other thing is that, of course, the Antarctic surface is not monolithic. There are ridges and crevasses, etc. And then also radio from ultra high energy cosmic rays hitting the surface is also accompanied by so-called transition radiation. If the ultra high energy cosmic ray core hits the surface, it will produce so-called transition radiation or stopping radiation. And as Hamlet said, there are more things in heaven and earth that are dreamed of in your philosophy. So those are the caveats to keep in mind. I'll mention that what we did, and I'll go through this quickly. So we were aware, for instance, of this problem, and what we did is we constructed an experiment called HiCal, which basically flew behind the needle balloon, and it sent out a pinging signal that was measured both in terms of its direct path as well as its surface reflected path. So this is a way of trying to calibrate the effect of surface reflectivity. The azimuthal detector on HiCal was actually built at MIFI. And what we found is that if we were to make a plot of the surface reflectivity for Antarctica and compare that with the expectation from the well-known Fresnel coefficients, we got very good agreement between the expectation and our data. So that seems to exclude the possibility, or at least make less favorable or less probable the possibility that what we're seeing is in fact some surface reflection effect. Okay, so what are the other possibilities? Um, People have looked at the possibility that what might be happening is that when the surface, or sorry, when the current from the air shower core intercepts the surface, it produces this stopping radiation, and this stopping radiation produces a so-called transverse current, which generates an RF signal at the balloon. That possibility has not been excluded, and that remains a viable explanation and possible explanation for the Anita mystery events. There are other possibilities that have been offered. Before getting to that, let me mention the most recent result from Anita 4. So Anita 4 has now seen a total of 4 additional so-called mystery events with a total significance of 3.2 sigma, and this was just released actually within the last couple of months or so. So now the total tally of mystery events is 1 from Anita 1 from Anita 3, and now 4 more candidates from Anita 4. What is interesting is that the Anita 4 events, unlike Anita 1 and Anita 3, are almost at glancing angles. So they're very, very close to the horizon. Now, it's been suggested that these events might be the result, the mystery events might be the result of a so-called subsurface reflector, that you take a conventional ultra-high energy cosmic ray and you take radio from that ultra-high energy cosmic ray, and it's just reflecting off of not the surface, but a subsurface feature that has an index of refraction characteristic such that you don't get an inversion. We've actually modeled this, and this is the paper which offered that possibility. We've actually modeled this possibility using Anita and HiCal data. What's shown in the bottom is the expectation that you would expect to see if you had, for instance, initially a surface reflection and then a subsurface reflector. You would see first an inverted echo and then a non-inverted echo. So this thing all the way on the right is what the authors are proposing Anita might be seeing. We did a statistical analysis. I don't have time to go into it, but I will say that we did a statistical analysis. Everything to the lower right is stuff that disfavors a subsurface reflector model, and is consistent with just conventional physics. Everything up and to the left is our data that would favor the subsurface reflector model. So clearly, all our high cal data disfavors and would otherwise contradict the idea of a subsurface reflector model.
Excuse me,
Okay.
Dave, you have
Yeah.
5 minutes
Okay.
left.
Okay. All right. There's been suggestions that these events might be due to the triboelectric effect. Masha Mikhailova spoke about this on Tuesday. This has been observed, for instance, in the rice and ore experiments at the South Pole. However, that statistical analysis has not yet been conducted with the needed data. It appears from a first glance that the events that we've seen, the mystery events, are not due to a triboelectric effect. Okay, I'll finish by just mentioning an additional technology that might be used to detect ultra high energy showers, and this is this radar technique. So here, for instance, there was a test beam experiment at SLAC where you took a test beam that generated a shower. There was a transmitter, and the transmitter produced an echo off of the shower itself, and that echo was observed in the time domain. So what's shown here is the echo off the charged particles in the ultra high energy shower cascade. You can also represent that in a spectrogram. This bright spot here corresponds to the time when the shower or when the observed echo was brightest, and it also corresponds to the time when the shower development within the target in the test beam environment should have been fully mature. So we see very strong evidence for these echoes. And moving forward, there's actually an experiment which has been approved to deploy a prototype test, sort of a test bed experiment in Antarctica at Taylor Dome, and that will happen around 2023. Okay, so future experiments. ANITA 4, the ANITA series is done. There's just been a proposal submitted actually yesterday for the next generation of the synoptic balloon-borne strategy that's called PUEO. And that will reduce the trigger threshold from an SNR of 6 to SNR of 2. We expect an Antarctic flight of 2024. And again, I just mentioned the radar experiment, Taylor Dome, in 2024. All right, and I'll just close with one final slide. So where is everything going in the future? Well, there's basically one future direction, and that's the IceCube Gen 2 experiment. The IceCube Gen 2 experiment is a successor. Dimitri mentioned this. It's a successor to Gen 2, and it will have a coverage, at least in terms of the optical array, of about maybe, as you can sort of read off this slide, maybe 4 to 6 square kilometers. So this is the footprint of the current IceCube. Just to the left of it is the planned footprint of the IceCube Gen 2 optical array. And in addition, there is a very large scale radio array which is proposed. This is Gen 2 radio. This will be about a $50 to $60 million, maybe a $50 million endeavor. It is massive. It will include 800 ice holes drilled in the ice over a footprint of about 500 square kilometers. So the plan for Gen 2 radio is that it will be large enough so that by almost all models, it should be able to detect something like 10 cosmogenic neutrinos plus. Sorry, that 10 number includes both cosmogenic neutrinos, and it should also have sensitivity to the very high end of the astrophysical neutrino spectrum as measured by IceCube Gen 2. That is to say, it should have a threshold that starts around 10 PeV, and it should extend all the way up into 10 and 100 EeV and beyond. And I'll stop there and thank you for your attention.
Hey, thank you very much for this very nice talk. So we have time for questions now. several questions. No questions.
I can ask one. So how deep do these holes need to be for the radio array?
So this is a question which is not simple to answer. So the upper 100 meters of the ice in at the South Pole has not yet reached its asymptotic density. It's called Fern, and because of that, the horizon or the ray tracing is limited. So you do best when you deploy your hardware at a depth of say 200 meters. There, the ice has its maximum density, but above 200 meters, the ice has not yet reached its full density, and ray trajectories curve by Fermat's principle. So the best depth from a standpoint of visibility is to go down to 200 meters. However, the logistical impact of deploying, so much hardware, 800 holes to 200 meters is obviously much more substantial than deploying to 100 meters. So from a science standpoint, I think it's clear that you'd like to go down to 200 meters if possible, and certainly the drill we have can get us down that far. However, from a logistical standpoint and the impact that this will have overall on the operations at South Pole, it may be that we'll be limited to 100 meters, or in fact, it may even be the case that there'll be no holes and ultimately will be limited to a surface deployment. So in getting to that final answer, there's going to be a balance between the science drivers as well as just the logistical boundary conditions and restrictions within which the experiments are operating.
Thank you.
You're welcome.
Okay, so I see one question in chat. Can you see this question, Dave?
No, I can't.
So the question is from sorry if I pronounced not correctly. Mohammed Fu Hassan Sheikh. How do you differentiate between direct signal and in ice signal if the polarity is the same?
How do you? Because yes, the polarity is the same, but our reconstruction, our angular reconstruction, is about 0.3 degrees. So we can clearly tell if a signal, we know the arrival direction very well, and we can tell whether or not the interaction happened, for instance, in the atmosphere, because the horizon relative to the balloon is at an elevation angle of about 6 degrees relative to the horizontal. So at an elevation of 38 kilometers, you look down, and the horizon is 6 degrees below horizontal. So anything above that, for instance, 5 degrees, as in the picture that I showed you before, we know is coming from a direct signal. Below that, it's coming from either a reflection or an upward coming neutrino. But ultimately, it's because the angular resolution is, like I said before, about 0.3 degrees.